Okay, so we're going to be doing a bunch of implicit differentiation questions, kind of like what I did with the video on a bunch of chain rule questions. And basically, I'm just going to give the introduction here. Implicit differentiation is kind of like chain rule in disguise. Remember that y and x are actually now appearing on both sides of the equation, maybe in y is appearing in some equation. It's an implicit equation because it's not explicitly defined as y equals something in terms of x. It's always going to be like y squared, it's going to be sine of y, any type of that. So we're going to be working with implicit differentiation. And like always, with the last video, I'm going to take it a slow pace to begin with, and then maybe I'll start speeding up towards the end. And if you ever feel like you can go faster than me, then I encourage you to do so, because that's basically, it shows that you know what you're doing and you don't need someone to help if you just know how to do it right away. Let's begin. Question 1. So in all these, we're going to try to find dy dx. So our first one is x squared y plus xy squared equals 6. That's our very first question. And I'll walk this one out really slowly since this is our first example. So remember, like in algebra, we can take things on both sides, like adding 5 to both sides of the equation. We can actually do that with derivatives. We can take the derivative of both sides. So the derivative with respect to x of this is equal to the derivative of 6. And we already know the right-hand side. The right-hand side is actually really easy. It's simply just 0. But the left-hand side actually involves a lot of work. Because x's and y are kind of related to each other, y is a function of x, we need to kind of treat y like a function that's like in terms of x. So the way we do it is, I notice that I have to use the product rule here, because it's a product of two functions if I were to treat y as the function. So let's do the product rule. So I'm going to bring this a little bit over, maybe here. Derivative, let's look at the first term only. So I'm going to do that in red. So the derivative of the first term and then keep the second the same, right? That's what the product rule, and then you want to keep the first the same and then take the derivative of the second, right? What is the derivative of y? We don't know. So the way you would write it is derivative of y with respect to x, right? We don't know it. Another way you can write it, which I kind of find much better, is just y prime. But you just have to keep track that you're putting primes there, because it might get mistaken as like a power, or you might just forget it. So right now I'm just going to put dy dx, and then later I'll transition to y prime. So that was the first term. So now we want to add the second term. Add the second term, this term. I'm going to do it in purple. Another product rule. So take the derivative of the first, keep the second the same, and then you want to add the kind of reverse role. So keep the first the same and then differentiate the second. What is the derivative of y squared? This is kind of like the chain rule, because y is the inner function and something squared is the outside function. So the derivative is 2y, and then we want to 2y to the first power, and then we want to find the derivative of the inside, which is just the derivative of y, in other words dy dx. And then we've successfully found the derivative of both sides. Now we just want to start simplifying, and the way we simplify is we want to group all the dy dx on the left side and then bring all the terms that don't have that on the right side. So what I noticed is that, let me write in highlighter, this is a term and this is a term, right? Anything that's being multiplied is a term, so we have to keep these on this side of the equation. The rest I'm going to move over by just subtracting it from both sides of the equation, right? So I'm going to bring it to the right. In other words, we have this term, right, the highlighted term, plus, let me just, this should be, no, I'm just going to get rid of that 1 there because it looks like a prime. So then plus x, or let me just write it as 2xy, and then we have dy dx. And then what do we bring on the other side? We brought minus 2xy, right? I subtracted it from both sides, and then subtract y squared. Usually I kind of also like to box what has dy dx so I don't lose track of where they are. So I know which ones I have to bring to the right side and what I have to keep. So moving on, let's see if I can scroll out just a little bit. That's quite a lot, but there we go. That's good enough. So now we have groups of dy on the left side and then not dy dx on the right side. And the aim here is to simply just factor out the dy dx. So I'm going to factor out the dy dx on the left hand side. So dy dx times x squared plus 2xy, right, is equal to negative 2xy minus y squared. And our goal is to actually find what dy dx is. And by factoring it out, we can simply just divide both sides by x squared plus 2xy. So this cancels out with this, and we're left with dy dx, and that's where we get our answer. So it's equal to negative 2xy minus y squared, all divided by x squared plus 2xy. And there's our answer. We found the derivative of the function, or we found dy dx, the formula for to find the slope at a point of this implicitly defined function. And the way we did it was just by treating y as kind of like a function of x, but also looking at it, especially in this section, this second term, where I had to treat it as a chain rule because y is a function of x. So you take the derivative of the outside and then you want to multiply by the inside. That's why I called it the chain rule in disguise, because y can actually act like a chain rule. So with the next problems, I'm going to write it in the y prime instead of dy dx because I find it much more easier to write. So let's continue. We have, let's do this one. We have x squared, or no, not x squared, x cubed plus y cubed is equal to 18xy. And I want to find dy dx. That's what we're going to do for every single of these problems. Find dy dx. That's not terribly difficult. Remember, the first step is to find the derivative of both sides. Um, 18x minus y, there we go. So now we just find the derivative with respect to x. And let's see, the first term, the left hand side looks a little bit more easier, so it's just 3x squared plus, and then we have to apply the chain rule with this y term. It's 3y squared times the derivative of the inside, which is y, the derivative of y, which we don't know, so it's just y prime. And then the other side, the right hand side, we have to apply the product rule. So 18 will be our first one, and then y will be our second function. So take the derivative of the first, keep the second the same, and then keep the first the same, take the derivative of the second. It's y prime. Now our next step is to group all the terms, right? Group all the y's, so I'm going to box them in highlighter. We have this term, and we have this term. And now I want to bring them to one side of the equation. Let's bring it to the left, because I typically do it to the left. And then so that means we have to bring this over, and we have to bring this over, right? So now we have 3y squared times y prime minus, right, I'm bringing this over, 18xy prime is equal to 18y, and then I brought over 3x squared. And then now I can just factor out a y prime, 3y squared minus 18x, and then we keep the right hand side the same, and then I solve for y prime. Y prime is precisely equal to 18y minus 3x squared, all divided by 3y squared minus 18x, and we're done. This is the answer. So let's move on to the next one. Okay, scrolling down, let's see, scrolling down to question 3. Keep writing in highlighter accidentally. 3, what do we have? We will work with this function. Y squared is equal to the quotient of x minus 1 divided by x plus 1. And you see that this one actually looks complicated on the right side more than the left side, right? But luckily there's no y's on the right side, so it looks a little bit easier because it's just a quotient rule, right? We know how to apply the quotient rule. So we want to find the derivative of both sides, derivative of this, and then it's equal to the derivative of the whole thing. And then from here, let's see, I want to find the derivative of the left hand side, which looks a little easier. It's just a chain rule, 2y to the first power, and then we want to multiply by the derivative of the inside, which is y, so the derivative of y is y prime. Another way you can think about this is anytime you differentiate something with y, you just tack on a y prime at the end. And that's also helpful to remember sometimes. Maybe if you don't like the explanation of using the chain rule, maybe just remember tack on the y prime at the end. And then the right hand side, we are going to be using the quotient rule. So the quotient rule says you want to find the derivative of the, let me just actually do it here. The derivative of the top, or the top is this one. That means the derivative is 1. And then the bottom is x plus 1. And the derivative here is also 1, and then we just apply the quotient rule. You want to differentiate the numerator, keep this one, and you have to do it in this order. You cannot differentiate the denominator first, because then your sign will be messed up. So this is why I don't really like using the product or the quotient rule, because you actually have to remember which one you want to differentiate first. If you don't want to use the product rule, you can actually rewrite this as this is just an aside. You can rewrite this as this function to the -1, and they're the same thing. And then you will have to apply the chain rule, which I find a little bit easier than the quotient rule and the product rule together. If you don't want to do that, you have to use this formula. So differentiate the top, which is 1, and then keep the second the same. Subtract, I guess, keep the top one the same and multiply by the derivative of the second, which is 1, and then we're going to divide by x plus 1 squared. And then we have to solve for y prime, and that's easy because y prime is, this is the only term with y prime, so that means I just do y prime and divide 2y from both sides, so it's x minus 1. X plus 1 minus x plus 1. I distributed the minus sign, and see that this cancels out with this. And then if I divide by 2y, then 2y appears here. So in all, it's just equal to 2y x plus 1 squared, and I see 2 cancels out with this. So y is equal to precisely this. There we go. On to the next one. Alright, let's try number 4 again, because something happened and I had to cut the video. So let's continue. So this is our function, or implicitly defined function. X squared equals this thing, this quotient looking thing, and it looks very, very complicated, right? You have y on the top and y on the bottom, and you're taking the derivative implicitly because y has to be implicit, all that. So it looks like a lot. So let's take this step by step, and with this problem we have to be extremely careful with how we copy things over, because if we make one mistake, the whole thing goes wrong. So we have to be really, really, really careful. So this is where organization comes in really handy. So the right hand side, I have to do quotient rule. I mean, if you really wanted to, you can do product and chain rule, but that's also a good way to go through it. But let's just do the quotient rule for practice, right? So the numerator is x minus y. The denominator is x plus y. The derivative of the numerator is 1 minus y prime, right? Or the derivative of y, which we kind of don't know, so that's how we kind of represent it as derivative of y. And then the derivative of the bottom is 1 plus y prime. So let's input it into the quotient rule formula, right? Derivative of the first, keep the second the same, minus the first, derivative of the second, all divided by g squared. So let's copy that over to the problem here. See, f prime, so we have to be really careful here, 1 minus y prime times g, which is x plus y, subtract f, which is x minus y, and then multiply by g prime, which is 1 plus y squared, all divided by g squared, which is x plus y squared. Okay. Now it just looks very interesting, especially because now the next step of implicit differentiation is to solve for y prime. So that looks kind of complicated because y is here and in a fraction. So let's make things more easier to look at and just multiply both sides by the denominator, right? This is not a y. I just saw. Okay, so in other words, it's 2x, x plus y squared is equal to 1 minus y prime multiplied by x plus y minus x minus y 1 plus y prime. And now we have to go through the task of, I guess, simplifying this down, because there's no way to solve for y without, I guess, simplifying this through, I guess, FOIL or any type of multiplying together distributive property. So 2x, x plus y squared equals, I'm going to bring this down now, all the way down here, because we'll need all this work just to find the derivative, or just to expand this. Let's see. Using FOIL, so I'm going to take this first term right here, it's x. It is, oh, did not mean to scroll to the right. Let me just try to get back. Let me scroll a little bit this way. There we go. X, and then we have, let's see, plus y minus x, y prime minus y, y prime. We have to be super, super careful with this, especially with our algebra, because it can get really messy. And if you lose track of stuff, then you're just going to make a mistake. So here we have x, and then plus x, oops, that's not an x, x, y, and then minus y, and then minus y, y prime. And then we just simply simplify this further just by removing the parentheses. I just did it for sign, just keeping track of the sign, especially here. A lot of people forget that this negative actually has to be distributed to every single term. So it's minus x, y prime plus y, y prime. And we see that stuff just starts to cancel on the right hand side, and it makes our life a little bit much more simpler. So we have this and this cancel. What else? Oh, the y's. This cancels with this. Anything else? Doesn't seem like it. So let me just simplify this further to 2y minus 2xy prime is equal to 2x x plus y squared. So now we have to solve for y prime. That shouldn't be too bad, right? Get all the non-y primes on the left side. Right? That's what I did. And then divide everything by negative 2x. In other words, y prime, I'm just going to write down the right here instead, is 2x x plus y squared minus 2y, all divided by 2x. And I guess if you really want to take one step further, all the terms have a 2 in common, so I can just get rid of that. And we are basically done. So this is the answer, and notice that it took a very long time just to get to one simple statement. This is one of the harder examples of implicit differentiation, mostly because it's an organization type of thing. So as long as we stay organized and be really, really careful with what we're doing, we'll always get to this answer at the end. So here's the answer, and let's move on to the next one. Number 5, we're going to start looking at trigonometric ones. I keep writing in highlighter. We're just going to look at a simple statement. X is equal to sine y, and I still want to find y prime. So, like always, find the derivative of both sides. And then the left-hand side is easy, it's just 1. And the right-hand side we have to apply implicit differentiation or the chain rule, basically. So this is the inside function, so keep it like that. Cosine is the outside, the derivative of the outside is cosine. Keep the inside the same, and then multiply by the derivative of the inside, which is y prime. And then we just solve for y prime, right? Y prime is equal to 1 divided by cosine of y. I guess if you really wanted to, it's secant, I believe. Secant y? Yeah, secant y, and we're done. So, trigonometric ones, this one was a simple one, but let's move on to some more trigonometric related ones. Number 6, x equals tangent of y. So we're switching the function to the tangent now. So again, find the derivative of both sides. So this is 1, the left-hand side. and the right. So the inside function is y, the outside is tangent. So the derivative of the outside is secant squared, keep the inside the same, and then multiply by the derivative of the inside, which is y prime, and solve for y prime. Y prime is equal to 1 divided by secant squared of y. In other words, it could be written as cosine squared of y, if you really wanted to. Now you just keep moving on, right? That one was a simple one. These two were simple. Let's keep building on with this. Let's add some more to it. X plus tangent of xy is equal to 0. This one's a little bit more complicated from first glance, because I see there's a product of two functions that are bound or kind of related to x. So again, but we still have to do the same process. Find the derivative of both sides with respect to x equals 0, right? The derivative of 0 is still 0, so I'm just going to already evaluate that derivative easily. The left-hand side is going to be a little bit more complicated, right? So it's 1 plus, so this is the chain rule. This is the inside function, keep that in mind. So the outside is tangent, so it's secant squared of keeping the inside the same, and then multiply by the derivative of the inside. And the derivative of the inside, we have to apply the product rule. So 1 plus secant squared of xy times, let's see, differentiate the first, so it's 1, and keep the second the same, plus keep the first the same, differentiate the second, y prime is equal to 0. And then we just solve for, this should be in parentheses because you're multiplying this whole entity, so it should still be in that entity as I like to think of it as. Now you want to solve for y prime. I noticed that, let's see, I see that this whole term is actually y prime. So let me just do that. Secant squared xy times 1y plus xy prime is equal to -1. And then how do I solve for y prime? Let's see. I guess the best way to go about this is actually distribute the parentheses. Secant squared of xy times y. So I'm just going to stick the y here, right? This here and this here. Plus, I'm going to put the term here and then write the trigonometric one here. And then now it looks much easier to solve for y prime. I'm going to scroll down from here. Okay, so this goes to the right side. So xy prime secant squared of xy is equal to -1 minus y secant squared of xy. So I just brought it to the right side. And then I can just divide everything out that doesn't have y prime attached to it. So y prime is equal to -1 minus y secant squared xy, all divided by, right, so this and this, x secant squared of xy, and nothing cancels out because there's subtraction symbols here and we can't. If there are multiplications or multiples of each other, then we can. So let's continue on with the next one. We're going to look at number 8 now, and with these next 3 we're just going to do 3 more. We're going to be focusing on finding the second derivative, or d squared y over dx squared, otherwise known as the second derivative. And we're going through the process of this, so we're going to start with this first one. It's just an equation of a circle. So the same process goes here. We want to find a derivative of both sides. Right, and then we want to just apply, I guess this one's easy, and then we have to apply the chain rule here, 2y, and then the derivative of y is y prime is equal to 0, and then solve for y prime, right? We've done this many times. Let's see, I bring the 2x over and I divide by 2y, I just did it all in one step, it's equal to -xy. I want to find the second derivative, which is the main point of this problem, not really the first derivative, because that one was actually much more simpler. To find the second derivative, we have to take a derivative of both sides again. So we see on the left hand side is actually the second derivative already, y double prime, and the right hand side we have to apply the quotient rule. So let's go ahead and do that. The quotient rule will basically say Okay, so let's let the top be negative x and the bottom be y. That means the derivative of the top is this negative 1, and the derivative of the bottom should be a g is y prime, and then we just fill it in, right? So I'm just gonna write what the result is here. It is, let's see, so f prime, which is negative 1, so negative, and then negative g prime, or negative g, so it's negative y, minus f, which is negative x, times g, which is, or g prime, which is y prime, all divided by g squared, which is y squared. And from here, we actually can take a result we just did right here, this result. And this is the key point I want to make, is that we take a thing that we learned in the past to substitute into this formula. So notice that this term here is y prime. And what I want to do is basically substitute that there. So y double prime is equal to negative y. I guess I'll change this to a plus x because this makes it plus. So plus x, and then multiply by y prime, which is negative x divided by y, all divided by y squared. And I can simplify if I really wanted to, but I'm just going to stop here because there's no point in making a mistake later. So here's our first one, and then first example of second derivative, and let's move on to problem, what is this, 9. Okay, problem 9. Let's see what we're going to do. Problem 9, we're also going to find the second derivative, and let's do it of this function, y squared plus 2y equals 2x plus 1. So I'm going to scroll down just to show all of problem 9. There we go. Like always, take the derivative of both sides, and we have to apply implicit differentiation. So 2y, oh wait, I'm getting ahead of myself here. Let me write this out. There we go. And then we evaluate this derivative, so it's 2y, derivative of the inside's y prime, or derivative, or dy dx, whatever you like. And then this one's just 2y prime, right? There's no power here, so there's not really an inner function, it's just a constant times the derivative of y. And then on the right hand side is just 2, right? Derivative of 1 is 0. And then we go ahead and solve for y prime. All the y primes are on the left side already, and all the things that are not already on the right side, so I just have to factor it out. 2y plus 2 equals 2, and in other words, y prime is equal to 2 over 2y plus 2, and I guess simplifying it to this, because all terms on the fraction have 2 in common, so I just took 2 out, or kind of divided every term by 2. So we have our derivative formula here, dy dx, but we want the second derivative, d squared y, or this d squared y dx squared, which is equal to y double prime. It's just another notation. So again, we could see this as a possible quotient rule, but I'm not going to do a quotient rule. I'm going to rewrite this as y plus 1 to the negative 1, just for extra practice with the, I guess, the chain rule in a way. So it's actually the derivative with respect to x. So these are all the same notation, just written slightly different. This is what I want to find, so I'm going to scroll down from here. I'm going to keep this piece of information we just found right here at the top. So the inside is y plus 1, so the derivative is 1, or not 1, y prime, and the outside is something raised to the minus 1, and then the derivative of that something is minus 1, and then x to the minus 2, and then I just plug it in. So the differentiation thing of this is precisely f prime g of x times g prime of x, which is equal to, see, f prime is negative 1, or negative y plus 1 to the negative 2 times the derivative of the inside, which is y prime. And we found what y prime is, right? I just did it right here, so we can substitute that in, which is negative y plus 1 to the power of 2, negative 2, multiplied by 1 over y plus 1, and that's it, right? You don't have to worry about, I guess you don't have to worry about simplification, but if you were, I guess the way you would write it is -1. Since this is like a over 1 and change it to a positive, it would be -y plus 1 to the third, or like that. Okay, so here's our last problem, question 10, and this one looks really intimidating, especially because we have to find the second derivative, or d squared y over dx squared. That's the notation, which is basically just find the second derivative, or y double prime. And we have to do this with an implicit equation, and this one looks very complicated, so let's try to do this one. So like always, we have to find the derivative of both sides of the equation. And I'm just going to evaluate the right hand side. It's already 0, right? Derivative of a constant is 0. And now the left hand side, let's see, apply the power rule and the chain rule if needed. And we have the same thing here. And we have to tack on that y prime, because it is implicit differentiation. Y is a function of x equals 0. And then from here, what can we do? We have to solve for y prime. So this term has y prime, so that means I'm going to bring this over. Y, or let me write it like this. 2/3 y to the -1/3. Y prime is equal to -2/3 x to the -1/3. And we see that this cancels out with this. Y 1/3. Oh, and I'm just going to divide actually by y to -1/3 to both sides. So that means y prime is equal to negative, we can't forget this negative sign, x minus 1 over 3 divided by y to the minus over 3. And I guess I can make this more simpler looking, as simple as you can, I mean. And doing that. So let's see. So that is the first derivative, or dy dx. We want to find the second derivative. And how do we do that? Well, we have to take the derivative of both sides again. Okay, so let's do exactly that. I'm going to scroll down all the way so you can see what we just found. Let's scroll a little bit up. There we go. And we want to find y double prime, which means we have to take the derivative of what we just found. So the derivative of this, essentially. And I'm going to zoom out because this is actually going to be a little bit of a longer type of problem. Right about here, let's zoom in a little bit. There we go. Alright, so let's continue from here. We want to use the quotient rule, right? Because y is on the top and x is on the bottom. Y is a function of x, so we have to use the quotient rule. So that means, let's do it. So the numerator, I'm going to make it -y to the 1/3. Remember, we can't keep this negative sign alone. We can't really, I mean, we can pull it out of the constant, but I'll just leave it like this, just for simplicity's sake. Let's see. G of x, or not g of x, f prime of x is -1/3 of y to the -2 over 3, right? Subtract 1, and then you tack on that y prime. You can't forget that one. G of x is going to be the denominator. I was about to say denumerator. And this one's 1/3 x to the minus 2/3. And now we just fill it into the quotient rule, which basically says this. And let's do that. Let's do exactly that. So it's equal to, we have to be really careful with copying everything down. I guess if I really want to skip a step, I can already plug this in. This makes it -1/3 y to the minus 2/3 multiplied by -y 1/3 over x to the 1/3, just to make it much more quicker. So that means we have f prime, which is exactly what I just did right there. -1/3 y to the -2/3 power multiplied by -y 1/3 x to the 1/3. We have to be super careful here, especially when copying this down. And then we have g, don't forget g. G regular, so x to the 1/3. And then subtract f, regular f, which is -y 1/3, especially with our sign. A lot of people make their mistakes with the sign. And then g prime, which is 1/3 x to the minus 2 over 3, all divided by g squared, which is x to the 1/3 squared, which I'll just write as x to the 2/3. Let's see if anything cancels out. Let's see, everything here is multiplying. This cancels out with this. That's nice. Let's see what else. Does anything else do anything? This changes to a positive sign. That's pretty good. This also changes to a positive sign. So there we go. That's and we can add these exponents together if you really wanted to. Let's do that. So negative 2/3 plus 1/3 is y to the negative 1/3 plus y to the 1/3 1 over 3 x to the negative 2/3 all over x squared. And here, I mean, you can even stop here if you really want to. I just wanted to make it look a little bit better because it looks pretty hairy or nasty looking. I guess I can take out the 1/3 and just make it like this. And I'll just stop right here. So this is the last step I'll take. 3x. So if you're wondering what I did in that last step, I saw that 1/3 was here and here. I factored it out, and if I factor it out, it appears like this. So I just brought the 3 to the why is this not erasing there? I brought the 3 to the denominator. So I guess I'll stop here. So this is y prime, and this is the second derivative of the function that we were looking for. And that means we've done 10 problems, so that's a lot of problems. I don't know how long this video will end up being, maybe around 30 plus minutes. And you can see it takes a long time because you have to stay really organized, especially with problems like these. If you did problem 4, that one was also a pretty difficult or long one. You just have to stay organized, and that's basically the whole idea of getting these correct consistently, is just how organized are you in your notation, and are you following the algebra principles, because the calculus itself shouldn't be that bad. It's just finding the derivative, power rule, product rule, quotient rule, chain rule. But the algebra used to like simplify and all that, that's where everyone makes the mistakes. And even I do from time to time. The algebra mistakes get me, not necessarily the calculus mistakes. It's more like the algebra mistakes that get me. So hopefully the more organized you get, the less amount of mistakes you get, especially in algebra, because there's a lot of minus signs thrown at you, and you have to make sure you're carrying the signs. You have to distribute the negative sign, you have to combine your terms, cancel out your terms, simplify their fractions. So just remember that, especially with this problem where we had to simplify here. So with that, that's the end of this video. I think this problem itself took 7 minutes. That was a long time. But that's the end of this video. Hopefully these implicit differentiation rules made more sense, or the implicit differentiation process makes more sense, especially with the second derivative. I know that can be hard sometimes. But that's it for this video.